All right, if you're in computer science theory, you've probably just accepted a certain truth without even thinking about it. Resolution is a weak proof system. It's just one of those things, right? Foundational. But what if that whole foundation is built on a bit of a misunderstanding? Today, we're going to uncover a hidden story, one that shows how this so-called weakness is almost always tied to some very specific and very critical restrictions.
Yeah, this is the myth we're going to deconstruct. It's a huge oversimplification that's been shaping our field for decades. You know, that's the kind of thing you hear in a lecture or read in a textbook, and you just kind of nod along. Well, today, we're going to poke some holes in it.
But here's the kicker. What if the famous landmark papers that proved this weakness weren't even talking about the powerful system we actually use in modern SAT solvers? What if they were all analyzing a hobbled, crippled version instead? That's the central mystery we're unpacking today.
Okay, so to really get to the bottom of this, we first have to understand that not all resolution proofs are created equal. It's kind of like a zoo of different proof structures. We need to get to know the different species because the details here, they're everything.
First up, let's talk about the heavyweight champion, general resolution. You'll often see it called a DAG, for directed acyclic graph. This is the real deal, the most powerful, totally unrestricted form. The key word here is reuse. Any logical step you prove, any clause you derive, you can use it again and again, as many times as you want. This freedom is exactly what makes modern SAT solvers so incredibly powerful. This is the system as it exists out in the wild.
And then, on the complete opposite end of the spectrum, you've got tree-like resolution. This is the most severe restriction you can possibly imagine. Every single thing you prove can be used exactly once. After that, it's gone. Poof. Think about how inefficient that is. It's like you have to reprove the existence of your great-grandparents every time a new cousin is born. You just have to do the same work over and over and over again, which causes these proofs to just explode in size.
And this really lays it all out, right? On the left, the general DAG is all about smart recycling, efficiency, reuse. On the right, tree-like is the model of inefficiency. Use it once, throw it away. So, as you can probably guess, proving that a tree-like system is weak is a whole different ballgame than proving it for the powerful DAG. It's not even close.
So between those two extremes, there's this middle ground called regular resolution. It's definitely more powerful than a tree because you can reuse some things. But it's got this one weird rule. On any single logical path from the start of your proof to the end, you can't resolve on the same variable more than once. So it's a step up from tree-like for sure, but it's still wearing some serious handcuffs compared to the full, unrestricted power of the DAG.
Okay, we've met our cast of characters. The powerful DAG, the crippled tree-like system, and the in-between regular one. So now, let's follow the paper trail. We're going to play detective and look at the landmark papers that gave resolution its weak reputation and see which of these systems they were actually analyzing.
Our investigation kicks off way back in 1985 with Haken's Big Paper. Then we jump to 1999, to this super influential work by Ben Sasson and Wiggleston. And after that, into the 2000s, where you've got folks like Razbarov trying to push the boundaries even further.
Let's start putting the evidence on the board. Haken's 1985 paper. This is the one that started it all. And yeah, it talks about resolution. But if you actually dig into the paper, his entire argument, the very math he uses, depends on the proof being a binary tree. His whole method falls apart without it. So boom, Exhibit A. The foundational proof of resolution's weakness was for a tree-like system.
Next up, a huge one. The famous short proofs are narrow paper. I mean, this is a cornerstone of the field. But guess what? To get their main result for the classic pigeonhole principle, their core theorem explicitly relies on the proof being tree-like. It's right there in the fine print. The pattern is getting clearer, isn't it?
And finally, let's look at the work from the 2000s. Now, researchers like Razbarov made a huge leap, no doubt about it. They moved beyond trees and managed to prove lower bounds for regular resolution. That was a major step forward, absolutely. But you see what's still missing, right? It's not the full, unrestricted DAG. They needed that no repeating variables on a path rule to make their arguments work.
So the pattern is it's undeniable. The foundational results that gave resolution its entire reputation for being weak weren't analyzing the system in its full glory. They were proving limitations on these crippled, restricted versions. And that should change how we think about this. But hold on, because the story is not over yet.
Just when you think you've got it all figured out, along comes this celebrated paper in 2018 by Part and Zamarit, and it makes a huge claim, a lower bound for a general DAG structure. I mean, this looks like it shatters our whole theory, right? Well, let's look at the fine print. And yep, there's a catch. Actually, a few of them. First, they weren't using plain vanilla resolution. They used a souped-up version with tools from linear algebra. Second, and this is the really big one, their argument only works if the problem is written down in a very specific, highly structured way. It's a heavy restriction, but they didn't put it on the proof structure, they put it on the problem itself.
So you see what happened? They didn't eliminate the restriction, they just moved it. It's like a shell game. The constraint shifted from the proof's structure to the system's rules and the problem's encoding. The Holy Grail, a truly unrestricted proof for a natural problem, remained completely untouched.
Which brings us to the final and maybe the most startling part of this whole story. After all this, what do we actually know about the full, pure, no-holds-barred DAG system? You know, the one that really matters in practice?
The answer is not nearly as much as you'd think. Proving whether this system is truly weak for the problems we care about is one of the single biggest open problems in all of proof complexity. The core question we all thought was answered decades ago, it is still completely, totally wide open.
And here it is, stated formally. For that classic, canonical pigeonhole principle problem, no one, not a single person, has ever managed to prove that it requires exponentially large proofs in the full general DAG resolution system we use today. We've proven it for all the crippled versions, but for the real thing, nope, still unsolved.
So, what's the final verdict? It means the next time you hear someone say, oh, resolution is weak, you're now equipped to ask the critical questions. On what proof structure and under what conditions? Because the story of resolution's weakness isn't about a fundamentally broken system. It's a story about brilliant researchers analyzing fragments of something far more powerful, leaving its true potential, for now, as a grand, unsolved mystery.